Hello. Okay, lesson 3. Lesson 3, I'm going to quickly go over the epsilon delta definition of a limit in such a way that it explains what it's about. I'm not really going to belabor the mathematical proving of it or using it as a proof, but let's just consider what it means. So the epsilon delta definition of a limit basically says if I have some function, okay, and there's some point on that function, all right? Is that okay? So if this function, it could be anything. Let's imagine it's a linear function. I just drew it poorly. So this is 0, 2, okay? Out here somewhere is a limit that I can test, right? And if I'm testing the limit of f of x as x approaches whatever, it could be whatever, you know, 1, 2, right? And the output, let's just see what it is. 3 times 2 is 6 plus 2 is 8, right? Okay? So if I'm testing the limit as x approaches 2 of f of x, and this line is f of x. What I'm saying, in a sense, is basically there exists, as I get closer and closer to 2, right? If I project that up, and coming from the left or the right, as I get closer and closer to 2 with my input, what will automatically happen, if the limit exists, is I will get closer and closer to the limit as my output. So you can see my output for 2 is here on the left and 2 is here on the right. You can see that? And what that creates is a box. And basically, as I squeeze this box more, it vertically squeezes until that box closes on the limit. That's really what the epsilon delta proof is about. I could belabor how you can take it's a very, very small number this way or that way. But look, it's a very, very small distance from 2 and a very, very small distance from the limit in its range. As that distance gets smaller and smaller and smaller, and so does the other distance. So the epsilon and the delta are connected. Nutshell. Epsilon delta definition. All right? So I'm going to take and let's do some limits together, understanding that always this is what's happening. And if I can approach a limit on left and right, then it's going to make an output box. And that's one of the things where if I'm not approaching the same output when I approach left and right, you know, my outputs are diverging or whatever, there's no box being created. So I have to converge, converge. If I converge, converge, I will become residing, I'll put myself residing on that point that the limit would exist at. Okay? All right. And that was epsilon delta. So you'll see like epsilon delta definition of a limit. It's really about that box. That's what the epsilon delta is about. That box getting smaller and smaller and smaller. All right. So here's a limit. What do you notice right away? I'm willing to bet you notice right away that the 7 minus 7 is a 0. Yeah? Okay. What's 7 plus 2 going to be? 9. Square root of 9 is 3. 3 minus 3, 0. So this is 0 over 0. True? And so I always do my plug-in first, because if it works, I'm done. I don't want to belabor something I don't need to do. So now that I'm in that position, I want to go ahead and try something else. What's the next thing I do? Next thing I do is factor, and then if that doesn't work, expand, and then if that doesn't work, table. Table is always my last resort. Okay? So I cannot factor, can I? And that's, again, my quick in-class scrawl. Because there's no way to factor this, right? I can't simplify it. I mean, everything's kind of together as it is. So therefore, I'm stuck with the table, right? So you do the table, pause now, set up the table where you think it should be. Take 2, 3, 4 minutes, get it done, and then check and see if it lines up with what I'm going to do. Okay, welcome back. So, I'm going to set my table up because at 7, I got undefined. And actually, did I get undefined? I actually got indefinite. But it doesn't matter. Either one of those is the same thing. It doesn't work, right? That's what it says. So, I'm going to try, because I think now you can see the patterns, right? So now that we understand they're either going to converge or diverge, let's see what they do. 6.99999, right, and 7.00001. So 1, 2, 3, 4, 5 decimal places, 1, 2, 3, 4, 5 decimal places. That's important. If you're just picking arbitrary numbers to do it once, a lot of decimal places, the same number of decimal places. That way your values aren't going to be confusing, where one is really approaching much closer than another. And if they approach quickly, if they're approaching slowly, it might not matter. But if they approach quickly, if I'm down here and up here, that might be a significant difference that might mislead you. So always try to use the same number of decimal places to help you with that. Plugging it into your calculator, here's what I say. I like to go through the steps, the syntax of the calculator. So 6.99, that's what I'm plugging in. In this case, 99999, whatever it is. I type that in, right? Okay. And then plus 2. Then I hit equals, because that whole value needs to be square rooted, not just the 2. Now that I've square rooted it, I can subtract 3, okay, and hit equals. And now that number is what the top represents. I use that equals key a lot. Now, if you've got a syntax calculator, you don't have to. But if you've got a little cheap $11 Solar, which is what I carry around, I don't carry a $100 calculator around. If I lose my $11 calculator, I'm bummed out. If I lose my $100 calculator, it's a little more than bumming, right? I'm very disappointed with that. But frankly, if I can sketch a graph in my head and I can use this calculator, it's just quicker. Most of the time I can get a sketch before someone can type it in. So what I get is, you know, some value, and then I'm going to divide that by 6.9999999 minus 7, which is going to be 0.000001, right? You know what I'm saying? But it's going to be negative because 7 was bigger than 6.99999. And when you get that, divided by, right? That's my output that I've got, divided by, I use my parentheses now. Parentheses, 6.999 minus 7, close parentheses, and then equals. But when I close the parentheses, I get that, right? So this is my output on top, and that's my output on bottom. My suggestion to you is this. Write that output down over a fraction bar, so you know what you got, okay? And then hit equals. Oh, sorry. I added a screen. I meant to advance the screen. Then hit equals. Okay? You hit equals, you're going to get your final answer. And that final answer was 0.1666667. Okay? Now you try the same thing on bottom, right? Instead of 6.99999, though, you're going to be putting in 7.000001. So I'll leave this up, hit pause so you have the structure, and just refresh yourself in your calculator skills. Okay, so let's see. I'm going to put in 7.0001, right, in both places. I'm going to get a new final answer in both places, right? This is going to become plus, right, because that's what happened. And this became plus, right? So I'm not rewriting it all, I'm just changing what changed. You've got it all written so you can follow this. And then when I divide it and hit equals, I got 0.016666666. What does it seem to be approaching? Are they both the same sign? Yes, that means they're converging. Right, the outputs are converging. That epsilon delta square is closing. As I close in on 7, it's closing in on 0.1666666. So I'd call this 0.16 bar. right? 1/6 repeating. Okay. All right, so that was your answer, sorry. 0.1, did I put my final answer? Well, my final answer is what it's converging to. How would I write that? I should have written L equals, right? L equals 0.16 bar. All right, next one. Okay, I've got the syntax there. Let me do this. Okay, let's have you try that. Let's see if your use of the calculator syntax yields these actual output values. Okay? That's what I want you to do. So you try it, and I admit it's tedious. And that's the whole reason I kind of dedicated this lesson to the use of your computer, or your calculator, I should say, making sure that you can do the table method accurately. If you can figure out, oh, I do the table method next, but you can't do it because you make calculator errors with fumbling fingers, what good is all that insight and knowledge when you can't make the calculator do what you think you're telling it to do? So your ability to express yourself to your calculator is important, right? You've got to understand how to speak its language. That's part of communication. It really is. It's just nonverbal. When you're communicating to your peers your ideas, it's verbal. But it's got to be in a way they can understand it. Otherwise, you have to rephrase it. And that's what you're doing with your calculator. Learning how to phrase it to get the output you know you want, and not hoping you get the output that's right. Okay, you try. Okay, let's pull down my slide. In fact, let's just get rid of it. Okay, and let's take a look at it. This is what I did. 1 divided by 4 equals, that's 0.25. Or you could just have changed that and used that easily. Plus, right? This is 1 over that, right? How did I do that? I typed in the value and then I hit shift to get to the 1 over x key. Right? And that's going to be in a different place in your computer. It might say x to the negative 1. It might say 1 over x. You might not have to hit shift. Depends on your calculator. But you're looking for that 1 over x, right? Or x to the negative 1, right? That's the same. So depending on your calculator, it would depend on what you're looking for. Okay? So x to the negative 1 is 1 over x. Then I do the bottom, I hit final, and I get negative 0.0625. Since I went from the left, negative side of 4, and from the negative 4, and from the right, positive side of negative 4, actually this is from the right now, and that's from the left, isn't it? Because it's a negative number, and that's an important thing to distinguish. Nevertheless, my left limit and my right limit are the same numbers, which means I do have a limit, and that limit is L equals negative 0.0625. All right. The precise definition of a limit, that's what I did with epsilon delta. Now, I'm not sure how that breaks down on here, but let's just touch it a little bit until it gets to be too mathematically heady that I don't really care about it, because I don't at that level. If you can't do the mathematical epsilon delta, but you understand what it means, you can figure out the limits. You don't need to prove the limit exists. You can find the limit and say, there it is, right? So it's important if you're a mathematician, but since most of you won't be, let's just see a little bit of what makes us understand. But that square, I think, is easy. If I compress towards my input, it compresses towards an output. It makes a box that becomes my limit. So here's a function. All right, f of a is the limit, right? Whatever the output is. That's a continuous function, so that limit would exist. And that's what epsilon delta is supposed to show you. Does a limit exist? So I'm using an example where a limit would exist. And if you take a look at this function here, this is part of how they set it up, right? So if you look at where this is and that output would be, so I'll leave that for you, and on the website I have some epsilon delta sample problems where they give solutions, those practice problems where they give you worked out solutions, and that's where you would go to do some epsilon delta practice. I'm not saying don't do it, I'm saying I'm not going to belabor it on this video. Alright? So that is the end of this lesson. Thank you.